In this video, we'll be discussing the concept of sound waves. First things first, let's take three important concepts about sound waves. Alright, number one, let's look at a definition for sound. By definition, sound is a form of energy produced by vibrating bodies. Okay, so we can define sound as a form of energy, and this energy is produced when bodies vibrate. Okay, so sound is basically a type or a form of energy, and it is produced when bodies vibrate. Number two, this vibration of sound wave causes a disturbance which travels out from the source of vibration in the form of longitudinal waves. So something else to note is that sound waves are also longitudinal waves. In our previous class, we defined longitudinal waves as waves which travel in a direction parallel to the vibration of the medium. Okay, so note that sound waves travels parallel to the direction of the vibration of the medium. Okay, the third thing to note is that sound waves travel through air, water, or solid. Now, what this means is that sound waves require material medium for their propagation, and hence we can say that sound waves are mechanical waves. So that's something to note. All right. So from here, we can note three things. Number one, a definition, which is that sound is a form of energy produced by vibrating bodies. Number two, the vibration causes a disturbance which travels out from the source of the vibration in form of longitudinal waves. So we can note that sound waves are longitudinal waves. Three, sound waves are mechanical waves. Now, by mechanical waves, we mean they travel through air, water, or solid. So we can say sound waves require a material medium for their propagation. Hence, we can say that in space where there is no air, sound does not exist. Hence, we cannot hear sound in space. A very important concept. All right. Now, let's look at something. If you say that sound waves travel, that means they must have a particular velocity. So let's look at the velocity of sound waves. Alright, so let's consider the velocity of sound waves. Now note that sound travels at a velocity. Alright, the velocity of sound waves is about 340 meters per second. Now this value is dependent on the author you're following. Alright, some authors will say that sound waves travel at 330 meter per second. Some will say 340 meter per second. But for this lesson, we're using the value of 340 meter per second as the velocity of sound waves. Now let's call this value V. So I'll call this V sound. V sound means velocity of sound. All right, it's equal to, we're taking that value to be 340 meters per second. So I have this 340 meter per second. Now, since sound is a wave, recall that in our previous class where we discussed the concept of wave, we have that if I'm given the velocity of wave, let's say V, velocity of wave, let me call this V. I'm given the frequency of a wave, I'll call this frequency, that's F, and I'm also given the wavelength. And if I'm given wavelength of a particular wave, so I'll call this wavelength. Let me put this as lambda. Recall that for any wave, that these three have a relationship. And the relationship is that the velocity of a wave, V, is equal to the product of its frequency, F, and its wavelength, lambda. So this becomes the relationship between the velocity of a wave, its frequency, and its wavelength. Here is your relationship. So here's our first formula in wavelength. Okay, that the velocity of a wave is equal to the frequency of the wave multiplied by the wavelength. Let's impute our unit for this. Note that velocity is measured in meters per second. Note that frequency is measured in hertz. All right, hertz, your symbol is Hz. I'll call this Hz. Note that lambda wavelength is measured in meters. So I'm having M. Alright. So this becomes the unit for each of the parameters. Now let's take some questions on this and then we try to solve this on sound waves. Question 1. What is the distance between two successive crests of a sound wave vibrating at a frequency of 455 millihertz in air? Velocity of sound in air is equal to 340 meters per second. Now, how do we solve this? As usual, our first task, write out solution there. All right. Let's look at the solution to this question. Our first task, as usual, is to list out given parameters. So let's list out the given parameters. What are we given here? The first thing we are given here, they said, what is the distance between two successive crests of a sound wave? When you hear the term distance between two successive crests, when we say two successive crests, what do we mean? Now note that two, or the distance between two successive crests, is known as the wavelength. All right, so wavelength, that's lambda, is simply the distance between two successive crests or trough. We discussed this in our previous class on waves. If you missed our previous class on waves, I'll leave a link to the class on waves. So check the video description. You'll see a link to get the video on waves. Now for this, we are asked to find this distance. So let's call this unknown. We are asked to find this distance unknown. Number two, they said vibrating at a frequency of 455 millihertz. So number two, we are given frequency that's F is equal to 455 millihertz MHz. We have this. Let's look at number three. Number three here, they said the velocity of sound in air is 340 meters per second. So we're given velocity of sound in air, or let's say velocity. Let's call this V as being equal to 340 meters per second. Alright, so I have this. Alright, so let's recall our formula. Recall that the formula for waves generally is that the velocity of any wave, which in this case is a sound wave, is equal to the product of the frequency of the wave and the wavelength. So you have this. Now, with this formula here, we are asked to find lambda, which is the wavelength or the distance between two successive crests. How do I get the value of lambda here? I'll divide here by frequency, divide here by frequency. This cancels this. So from here, we can have that this value here, lambda, is equal to V divided by F. That's equal to V all over F. Let's impute values. This is equal to, for V, what's the value? V is 340, it's a constant, all right? Velocity of sound in air is constant, 340 all over. For frequency, we're giving this as 455 millihertz. The term milli simply means 10 to the power minus 3. So it becomes 455, milli means times 10 to the power minus 3. That's milli, and then you have hertz. So we now have this as hertz. All right. Let's impute value. So this becomes 455 times 10 to the power minus 3. So we have this. Alright, so you take your calculator and punch this correctly. Alright, punch this correctly. What do we have? You have 340 divided by 455 divided by 455 times 10 to the power minus 3. If you punch this, your value here is 747.2525. We're looking for lambda wavelength, and we said wavelength is measured in meters. So this meters. So this becomes the answer to this question. We'll look at one more question on this, and then we'll go to the reflection of sound waves. Let's take one more question on this. Alright, question number 2, it says, what is the period of vibration of a sound wave of wavelength 256 centimeters? Let's solve this solution. Let's solve this. So first things first, let's list out given parameters. What's the first thing you're given there? You're given that the wavelength is 256 centimeters. So number 1, wavelength, let's use lambda, is equal to 256 centimeters. 256 centimeters. What are we asked to find here? We asked to find the period of vibration T. Number 2, period of vibration T is equal to unknown. And this is literally everything we've been given. Now, what do we know about period? We know that period T is equal to the inverse of frequency. All right, so period is equal to 1 over frequency. So my task here would be to first of all get the frequency, then after that, we'll now proceed to get the period of vibration. Now, having said that, how do we get frequency? Recall that our formula is that velocity is equal to frequency times wavelength. In this question, we're given the wavelength as 256 centimeters, but we're not given velocity. Note that, as we said earlier, velocity of sound in air is a constant, and we are using 340 meters per second as our value. Alright, so from here, let's impute the value of lambda, but before then, we'll convert this from cm to meters. So let's convert 256 cm to meters. What's our answer? What do? You simply divide by 100, so it becomes 256 divided by 100. And if you do this, you have your answer as 2.56 in meters. So this is how you convert from centimeters to meters. Alright, so we can now impute values. Imputing values here, we have that the velocity is 340. It's equal to the frequency, which is unknown, times the wavelength, and the wavelength is 2.56. So 2.56. To get the value of the frequency, I'll divide here and divide here by 2.56. 2.56 divided here by 2.56. From here, this cancels this. It means that frequency is equal to 340 all over 2.56. And if I do this division here, let's try this. 340 divided by 2.56. Our answer here is 132.8. 132. Okay, let's use two decimal places. 81 in hertz. Don't forget that we measure frequency in hertz. So we have this value as the frequency. We're asked to find the period, and we said period. Recall that period T is equal to the inverse of frequency. So T is equal to the inverse of 132.81. And if I punch this, I'll have 1 divided by 132.81, and that's about 0.0075. Right, so I have 0.0075 in seconds. So you have this. So basically, this becomes the period of vibration of the wave velocity. All right, so this is how we work on this. Let's look at the next concept, which is on the reflection of sound waves, which will now lead us into the concept of echoes. All right, so let's look at some of the properties of sound waves. Recall that in our previous class on waves, we talked about some of the properties of waves, which include the reflection of waves, the refraction of waves, the interference of waves, the diffraction of waves, and etc. So we'll take them one after the other, particularly for sound waves. Let's start with the reflection of sound waves. Now, by definition, in our previous class, we've already defined reflection as the change in the direction of a wavefront at an interface or at the interface between two different media so that the wavefront returns to the medium from which it originated. All right, that's the concept of reflection. Now, note that it is the reflection of sound waves or the reflection of sound that gives rise to the concept of echoes. All right, let's look at echoes and then take down some basic points about echoes, and then we'll proceed to solve problems on echoes. By definition, an echo is a sound heard after the reflection of sound waves from a plane surface. Okay, so you should take note that by definition, we define echo as a sound that is heard after the reflection of sound waves on a plane surface. So echoes are produced by sound waves when they reflect. So we can say that echoes are actually a product of the reflection of sound waves. Let's look at some key concepts about echoes. We'll look at two very key concepts about echoes, and then we'll proceed to solving problems involving echoes. Now, here's the first key concept. Note that echoes are affected by distance and can only be heard when the minimum distance between the source of sound and the reflecting surface is about 17 meters. Okay, that's our first concept. So the first key thing to know about echoes is that echoes can only occur when the distance between the source causing the echo and the reflecting surface is about 17 meters. And we'll look at this concept using a particular solving. All right, we'll derive this particular value and you see how we got the 17 meters. So that's the first key concept you should note. The second key concept you should note about echoes is that echoes can be heard separately from the original sound if it arrives at least 0.1 seconds later. Now, why is this concept important? If an echo arrives at the exact time as the original sound, then the echo would go unnoticed because the ear will not be able to differentiate between the sound and the echo because they arrived at the same time. In essence, for us to differentiate between the original sound and the echo must be heard at a later time after the original sound has been heard. And this later time should be at least 0.1 seconds later. That's the concept. So with these two concepts now, we'll proceed to getting some solvings on echoes. Now, here's the first thing. Recall that in our previous class, we said that velocity, which is v, is equal to displacement, or in this case, let's use distance. So distance d all over time. So that's time and that's t. All right. So we can say that v is equal to distance all over time. Now let's apply this to the concept of echo. All right. If you apply this to echo, so let me say applying to echo. Now, before we apply this to echo, let's look at something. Let's say we have a boy at this particular point here. We have a boy here. All right, so let's call this a boy. And let's say this boy here is at a particular distance from a wall. Let's look at this wall here. So we'll call this a wall. All right, so we have this. We'll call this a wall. All right, so this boy shouts or gives a particular sound wave. So he's shouting such that the sound wave moves from his mouth, all right, starts from here, hits the wall, which is at this point here, and then what next? It reflects. That means it goes back to the distance or the source from which it originated, which is the boy. So with this, right, it goes back to this. All right, what do you observe? Let's call the distance between the source, which is the boy, right? Let's call this is the source of the sound wave, which is the boy, because he's the one shouting. The distance from the source to the wall, let's call it d. Okay, so distance from the boy to the wall is d. Now here's what we can say from this particular equation, that v is equal to d over t. It is mathematically correct for us to exchange these two positions. What do I mean? It means time can go up here and v comes down. So time goes up here, we'll have that t is equal to d all over v comes down here, we have v. So we have this. In essence, we can say that time is equal to the ratio of distance all over velocity. Now, applying this to the sound wave concept, we can say that the time that this boy will take to hear the echo, all right, the time that this boy takes to hear the echo will be equal to not just d but total distance. So the time is equal to total distance traveled by sound waves. All right, so I'll call this total distance of of sound wave all over the velocity of sound in air. Of course, the boy is shouting in air, so I'll call this all over velocity of sound in bracket air, that's in air. So with this, we can say that the time t is equal to, let's go back to our diagram. Let's observe something about the total distance of the sound wave. Note that the distance of the sound wave from the buoy, which is the source, to the wall would be from here to this point, which we have said the distance is d. So I have my first d, but recall that this is not the total distance of the sound wave. Recall that for the buoy to hear an echo, this same sound wave must now travel back from the wall back to the buoy. All right, it must travel back to the wall, and these two distances are the same, so we can have a second d. In essence, the total distance traveled by the sound wave, let's call it capital D, is equal to the first distance that it moves from the source or from the buoy to the wall, which is this one up here, which we call a D. That becomes the first D with which it got to the wall, plus the second distance with which it moves from the wall back to the buoy, which we call a second D. And we are saying that if the buoy is stationary at the same point, then it has to be what there? The same value. So we now have a second D. Alright. This is the distance from the buoy to the wall, and the second one here is from the wall back to the buoy. In essence, the total distance D is equal to what there? 2 times the distance between the buoy and the wall. This concept is very important when working on echo. So note that the total distance traveled by the sound wave is usually equal to the distance of separation between the source and the reflecting surface. Okay? In this case here, the source is the buoy, the reflecting surface here is the wall. So in essence, bringing this back, we'll have that total distance of sound wave becomes d, capital D, all over velocity of sound. We said the value is 340. And if we break this down, this is equal to capital D is equal to 2 times the small distance, as we already explained, all over 340. And we said 340 is a constant, which is the velocity of sound in air. So we have this. So hence, we can say that T is equal to 2D all over 340. Now, here's our first equation on sound waves to note. That's our first equation. Now, again, we said that if you look at our second concept to note, let's go back to this. Look at the second concept. It said echoes can only be heard separately. Let me underline this. Echoes can only be heard separately from the original sound if and only if it arrives at a later time, which is at least 0.1 seconds later. In essence, the time should be greater than 0.1 seconds. So for echo, again, another condition, for echo, the time t should be greater than 0.1 second. Let's impute this value into our equation 1 and see what we get. From here now, we can say that this total value here, this time, we said time should be greater than 0.1 seconds, but the value of time here is 2d over 340. So time, this one here, which is 2d all over 340, should be greater than 0.1 seconds or 0.1. We now have an equation here that we would have to solve. How do we solve this? Of course, we'll solve this as we solve a normal fraction. This is all over 1. So we would have a cross multiplication. Alright, so let's cross multiply from here. I'll divide this here. Let's look at this. So from here, we can have that 2d times 1 cross multiplying. You'll have that 2d. The sign here is greater than, so greater than. From here, cross multiply these two, becomes 0.1 times 340. 0.1 times 340. What do we have there? This becomes 2d is greater than 0.1 times 340 is 34. That's a value. Let's get the value of d. To get d, I'll divide here and divide here by the coefficient of d, which is 2 and 2. This cancels this. So it means that d should be greater than, from here, 2 here, 1, 2 here, 17. All right. 34 divided by 2 gives you 17. So you can see that the distance before I can hear an echo should be greater than 17 meters. And this is how we got our first key concept. So from this point here, you can say that we need, or the distance between the source of the sound wave and the reflecting surface should be at least 17 meters before an echo can be heard. And this is exactly what we meant in our key concept one. Going back to key concept one, where we said echoes are affected by distance and can only be heard when the minimum distance between the source of sound and the reflecting surface is about 17 meters. So you can see how we got these key concepts. All right, so having said this, let's take some sample problem on sound waves and work on it, okay? Let's take some sample problem on sound waves and discuss them. Let's take the first example on echoes. The question here says, a boy standing some distance from the foot of a tall cliff claps his hand and hears the echo 0.5 seconds later. If the speed of sound in air is 340 meters per second, how far is he from the cliff? That's your question. Okay. Solution here. For this question here, our task as usual would be to write out the given parameters. So given here. What's the first thing you were given here? They said that a boy standing some distance from the foot of a tall cliff claps his hand and hears the echo 0.5 seconds later, which is this. So the first thing you're given there is the time with which, or the time after which, the boy hears the echo, which is t, and that's equal to 0.5 seconds. That's t for echo. What else there? They said if the speed of sound in air is 340 meters per second, well, that's a constant. So we already know that v, or speed or velocity of sound in air, is 340 meters per second. Now they're asking you, they said, how far is he from the cliff? You're looking for distance. Number three, distance d is equal to unknown. Now recall that for echo, what do we have? We have that velocity v is equal to d all over t as usual. But for echo, we said d, capital D is equal to what there? 2 times the distance, as we already discussed. That means v is equal to d becomes 2d all over t. From here, we have to find the value of d. What do we do? You can choose to make d to be subject of the formula 2d times 1 cross multiplying. I have 2d is equal to v times t gives you vt. So I have this. From here, divide this by 2, divide this by 2, this cancels this. So we can get d as being equal to vt, velocity, which is 340 times time 0.5. Velocity becomes 340, that's v, times t 0.5. This all over 2. This all over 2. And that's equal to, we have that d is equal to, let's impute this value. D is equal to 340 multiplied by 0.5. That gives you 170 all over 2. So we have 170 over 2, and that's about 85. So the distance there is 85 meters. That's the answer to the first question. Let's try one more question and then we'll look at something else for this class. Question 2 here says a sound wave emitted from the bottom of a ship travels at 1500 meters per second vertically downward through water to an ocean bed 260 meters deep and is reflected upwards. What is the time interval between the instant the sound is emitted and the instant the echo is received? Okay, so although it's a sound waves question, it's on echo. So always check if there's this mention of echo there, because this will determine the formula we use. So they mentioned echo here. Let's take down parameters. Okay, solution. Let's list out the given parameters given. What are we given in this question here? Let's go back to the question and see. They said that it travels at this travels at 1500 meter per second vertically downward. Meter per second tells you velocity. So the first thing I'm giving there is the velocity of the sound wave in water, that's V, has been equal to 1500 meters per second. What else? They said through water to an ocean bed 260-meter deep. All right. So we are saying that the distance between the ship and the ocean bed is about 260 meters deep and is reflected upwards. So number two, the distance between the ship, let's call this a small d, has been equal to 260 meters. That's the value. So in essence, what you're saying here is that I have, let's say, a water body here. I have a ship. The ship is usually immersed a bit into the water like this. Let's use it as a ship. This, and then we have, let's use this. All right. So this is like your ship. So this is the ship being immersed in water. So here's my ship partially inside water. You can see some part already inside the water there. Okay, and then this is now the river bed or the seabed. We have this as your seabed. Now they said the distance between the ship and the seabed, this one here is your seabed. Distance between the ship and the seabed, as given in the question here, is about 260 meters. That's your value. And they said this ship here, the term they use there, of a ship. All right, the ship is traveling at, so from here they said the ship is traveling at 1500 meter per second. So let's say the ship is going this way here. We'll call this u, and the value, okay, let me put it this way here. It's going this way. U has been equal to 1500 meter per second. Oh, let's use V. We're using V here. So V is equal to 1500. So this ship drops a particular sound. It goes to the riverbed here, reaches here, and then goes up again and echoes, comes back to the ship there. So we have this. That is like your diagram of the question. Okay. Now from here, we are asked to find what is the time interval between the instants. Okay. So we are asked to find time 3. Time t is equal to unknown. Now we know that for echo, first of all, we know that v is equal to distance or displacement over time. Velocity is equal to distance or displacement over time. For echo, we said d is equal to 2 times z, and we said in this case d is equal to 2 times the value of small d here is 260. 2 times 260. All right, so d is equal to 520. That's 520 in meters. So we have this. All right, from here we can now say that time or v is equal to 520, or we already have a value for v. So let me take this off. The value for v in the question is 1500. This is equal to this all over time. That's 520 all over time. So we have this. From here, this is all over 1. This times this becomes 1500. This times t is equal to 520. That's this times this times 1. From here I have 1500 t is equal to 520 times 1 is 520. I'll also divide this by 1500, divide this by 1500. This cancels this, so t it's equal to, I have this as let's say this 520 all over 1500. The time interval here would be 0.35, this one here, seconds. So the echo will be heard at 0.35 seconds later. So basically, this is the solution to this question. All right. Let's look at the next concept, something about echoes. Okay. So some application of echoes include number one, echoes can be used in the determination of the speed of sound in air. So that means we can use echo to determine the speed of sound in air. That's your first application. The second application of echo is that there's something called echo sounding. Alright, so echoes can be used in a concept called echo sounding. Now, what's echo sounding? Echo sounding is simply used, it's a method that is used to determine the depth of a seabed from a ship. All right, just like we did in example 2 there. So echo sounding is just simply a process that is being used to determine the depth of a seabed from a particular ship. That's it. The third thing we can use an echo for is the exploration of gas and oil. And then the last thing we can use an echo for is to detect the presence of submarines. You know that submarines are usually immersed in water and you may not be able to see them, all right, but you can use the concept of echo to detect the presence of submarine in any region in a sea. All right, so you can do your own research about how this works practically, but you could just note these four application of echoes. Number one, for determining the speed of sound in the air. Number two, for echo sounding, which is simply used to determine the depth of a seabed from a ship. Number three, the exploration of gas and oil. Number four, the detection of submarine. We'll end this class with a very important concept called reverberation. Alright, so let's look at a very important concept in the concept of sound waves known as reverberation. Okay, now note that reverberation is simply an effect, or let's say a negative effect of echoes. Let's look at some key concepts about the idea of reverberation. The first concept is that in concert halls and auditoriums where multiple echoes can sometimes be a nuisance brought about by the reflection of sound waves from the walls, the floors, and the ceiling of the hall, the echoes together with the original sound gives rise to long drawn sound which sometimes confuses the listener. All right, this continuous occurrence of echoes due to multiple reflection of the original sound is called reverberation. So this is the concept of reverberation. All right, it occurs in concert halls and large auditoriums where probably a singer is giving out a sound, and then since the distance between the singer and the wall or the end of the auditorium is more than 17 meters, you start experiencing the concept of echoes there. All right, sometimes the singer is done singing, but you can still be hearing his or her voice there. It's called reverberation. The second concept is that reverberation, by definition, is the persistence of sound after the source ceases. Right, a very key concept. So, by definition, reverberation is simply the persistence. So, you continue hearing a sound even when the source producing the sound has stopped. It's called reverberation. All right. Now, here's something to note. A place where reverberation occurs is said to have poor acoustical properties. All right. So, a place that has poor acoustical properties means that the place does not have enough properties that can absorb sound waves. And because of that, you tend to experience the concept of reverberation in such a place. All right. The third thing to note about this, which is the final thing, is that reverberation is reduced in halls by covering the ceilings and walls with soft perforated boards, which can minimize the reflection of sound waves by absorbing them quickly, or by hanging curtains round the hall and having more openings in the wall. So in large auditoriums, you see that these auditoriums usually have curtains, or if not curtains, you'll be seeing a lot of walls right around or in such auditorium. The concept is to reduce the concept of or the idea of reverberation. All right, so this is basically all we'll treat in this class 1. In class 2, we'll look at some other properties of sound waves, such as the refraction of sound waves, the diffraction of sound waves, and the inference of sound waves, and also the concept of beats. We'll explain all of those in our next class. So look out for Sound Waves 2 class, and then you can learn more about sound waves from that class. Alright guys. Alright, so you can try this question. A sound wave emitted from the bottom of a ship travels at 1480 meters per second vertically downward through water to an ocean bed 55,600 centimeters deep and is reflected upwards. What is the time interval between the instant the sound is emitted and the instant the echo is received? So solve this question and leave your answer in the comment section. Hint: This value here is in centimeters. So convert it to meters first. How? Divide by 100 and then use your formula. Solve this question. Leave your answer in the comment section and I'll tell you if you're correct or not. Alright? Alright guys, so if you enjoyed this video, as usual, hit the like button to like this video, leave a comment. For your comment, I gave you a task, solve the question and leave your answer in the comment section and I'll tell you if you're correct or not. If you're new here or you're yet to subscribe, please do all to subscribe and hit the bell icon, select all so that you get notified whenever we upload new content. And finally, do all to share this video to your friends so that they can also learn. Thank you and see you in our next class.